Hello, I'm Akinori Kawachi of Mie University. Today, let me talk about communication complexity of private simultaneous quantum messages protocols. This is joint work with Harumichi Nishimura of Nagoya University. The multiparty computation, MPC, is one of important protocols in the area of information theoretic cryptography. The task of MPC is to compute a function f jointly with parties who join the protocol by communicating each other. An output value of the function f can be computed from private inputs of parties. This is easy if they do not mind the privacy. However, an MPC protocol has to compute f without leaking any information except for the output value. To achieve such a cryptographic task, we are interested in how much overhead we essentially require in the protocol. In the field of theoretical computer science, including cryptography, the communication complexity of protocols has been often discussed to analyze the overhead. The communication complexity of a function f is the sufficient and necessary number of bits that parties communicate with each other to compute f in a protocol. However, general MPC has very complex communication pattern since many parties send the messages to each other back and forth. So, we focus on a simpler communication model than that of MPC to understand the communication complexity in cryptographic settings. The simultaneous message passing SMP model has a naturally restricted communication pattern. This model has been deeply studied so far in the area of communication complexity. In the SMP model, parties have their own inputs and common random strings among them, which we call R bits in this talk. Each of them generates a message from the input and R bits, and they just send the messages to the referee. The communication among parties is not allowed. In this talk, we suppose protocols has perfect correctness, namely, receiving their messages, the referee computes a correct output value of a function f with probability 1. The communication between parties and referee is one-way, non-interactive. Unlike the MPC model, SMP protocols do not mind the privacy condition. A quantum analog SQMP model has been also considered in quantum communication. The main difference from SMP is that parties and referee can manipulate quantum messages. So, parties generate quantum messages from their inputs and R bits, and they send quantum messages to the referee, and the referee can decode an output value of a function from the received quantum messages. Sometimes we consider a stronger variant with shared entanglement among the parties, instead of shared classical randomness. We call it E-bits in this talk. The SMP model and its variants do not mind the privacy condition, unlike MPC. A cryptographic model with the same communication pattern is called private simultaneous messages, PSM for short. In the PSM model, a protocol is required to meet the privacy condition like MPC. That is, The referee learns nothing from the messages except for the output value of the function. In this talk, we focus on the information theoretically perfect privacy in the protocols. More formally, there exist two distributions, D0 and D1, such that for every input x1, x2, and x3, the joint distribution of the messages is identical to d f of x1, x2, x3. This means the joint distribution of the messages depends only on the output value. So, the referee only learns the output value 0 or 1. In this work, we propose a new quantum analog of the PSM model, named Private Simultaneous Quantum Messages, PSQM for short. Like the SQMP model, parties and referee can manipulate quantum messages. In addition, a PSQM protocol has to meet a privacy condition. The notion of privacy can be naturally extended for quantum messages. There exist two mixed states, row 0 and row 1, such that for every input, the joint mixed state of quantum messages is identical to row f of x1, x2, x3. We also consider a strong version of PSQM protocols with shared entanglement instead of shared classical randomness, as well as the SQMP model. The two-party PSM protocol was first considered by Feige, Kilian, and Nauer in 1994. They provided a two-party PSM protocol for any Boolean function with information theoretically perfect privacy. Unfortunately, it requires exponentially long messages in input length. In 1997, Ishii and Kushilevitz considered a more general k-party setting, and they provided an efficient k-party protocol for any number L function. Following these initial results, many constructions of PSM protocols and its variants were studied, including those for specific classes of functions. Meanwhile, there are few results on communication lower bounds of PSM protocols. Recently, Applebaum, Horenstein, Mishra, and Shilevitz demonstrated communication lower bounds roughly 3 times n for two-party PSM protocols for random functions of 2n-bit inputs. It should be noted that 2n is a trivial upper bound for any 2n-bit function, if the protocols do not mind the privacy condition. Their result implies that the privacy condition essentially requires additional communication cost in PSM protocols. So, it is natural to extend this result to the quantum analog. Our first question is whether or not this additional cost is inevitable, even for PSQM protocols. In the theory of quantum communication complexity, many studies have examined the power of shared entanglement so far. For example, Gavinsky, Kempe, Regev, and Diouf provided some relation that demonstrates a gap between quantum entanglement and classical randomness. To decide whether a given pair of inputs satisfies the relation, roughly order L to 1/3 qubit communication is necessary for two-party SQMP protocols with R bits. But order log n bit communication is sufficient for two-party SMP protocols with E bits. These results imply an exponential gap of communication complexity with quantum entanglement and classical shared randomness. For the equality function, Hong and others demonstrated that 2n-bit communication is necessary to compute the equality function in two-party SMP protocol with R bits, but n-qubit communication is sufficient in two-party SQMP protocol with E bits. That is, they provided a factor 2 gap between them. This gap is best known for total functions. So, our second question is, what happens in the gaps if we add the privacy condition? For the first question, we prove the same communication lower bound as the classical counterpart shown by Applebaum and others. Specifically, we demonstrate roughly 3n communication lower bounds of two-party PSQM protocols with R bits for random functions of 2n-bit inputs. Therefore, even if we allow parties to use quantum messages, the non-trivial communication cost is inevitable. For the second question, we provide two results. Theorem 2 provides a factor 2 gap in k-party PSQM protocols for a total function between R bits and E bits. Specifically, we provide an explicit total function so that some PSQM protocol with E bits has kn over 2-bit messages, but any PSQM protocol with R bits requires at least kn bit messages. Thus, even under the privacy-preserving setting, the shared quantum entanglement reduces message length by half for a total function. Theorem 3 provides an exponential gap for a partial function. Specifically, for some partial function, we construct a two-party PSQM protocol with E bits of communication complexity at most order log n, and we show a communication lower bound of omega n for two-party PSQM protocols with R bits. So, the shared entanglement can reduce message length exponentially for a partial function even under the privacy-preserving setting. Now, let's see proof ideas for theorem 1, which provides a communication lower bound of roughly 3n for random functions of 2n-bit input. In the proof of the classical communication lower bound, we first run a PSM protocol twice independently. We suppose that a message M is generated by the first run, and M' is generated by the second run. Then, we focus on the event that these two messages collide. To prove the lower bound, we use the following fact that the collision probability is at least inverse of the message domain size. So, we obtain this relationship, and equivalently, the message length is lower bounded by this inequality. Therefore, our goal is to prove an upper bound of the collision probability. Let's try to apply the same strategy to the quantum case. We run a PSQM protocol twice independently, and we consider the collision probability of two quantum messages. Unfortunately, this probability is not lower bounded by inverse of dimension of the message space. Because infinitely many quantum states can live in the message space of finite dimension. So, we need a collision measure that has the desirable property to prove lower bounds. Our idea is to use the purity of quantum states as a collision measure. The purity is defined by trace of square of quantum states, and originally used for measuring how pure the quantum state is. Observing this definition, we can consider the purity as how much the quantum state is overlapped with itself, that is, how much two independent states collide. Actually, it is well known that the purity is lower bounded by inverse of dimension of the space, which corresponds to the fact about the collision probability in the classical case. And we can obtain a lower bound of quantum message length from this inequality. So, our goal is reduced to an upper bound of the purity. In the proof of the classical lower bound, the collision probability was analyzed by a combinatorial argument from the communication complexity. In the quantum case, we extend the argument to a combinatorial analysis of the trace. In the classical case, either a collision will happen or it will not happen, one or zero, but the trace can take on continuous values. So we need to deal with this barrier to complete the proof for the quantum case. Next, we will see the details of theorem 2. This theorem provides a factor 2 gap of communication complexity for a total function between E bits and R bits. The total function is actually a generalized equality function. As I told before, a two-party PSQM protocol with E bits was known for the equality function. This protocol sends n qubits in total for the equality function of 2 n-bit inputs, but it does not satisfy the privacy condition. We can construct a two-party PSQM protocol with E bits based on this SQMP protocol by random paddings to the quantum messages encoded by the Bell basis. This protocol can be also generalized to a k-party version. This GEQ function is a generalized equality function. Indeed, when k equals 2, this is exactly the equality function. We can also construct a k-party PSQM protocol with E bits that sends kn over 2 qubits to the referee in total. We can obtain the communication lower bound of kn qubits for k-party PSQM protocols with R bits from the argument of Diouf for the SMP model. Let me omit the details. As seen in the previous slide, theorem 3 provides an exponential gap of communication complexity for a partial function between E bits and R bits. The partial function is so-called distributed Dodge-Joda problem. For n-bit inputs x1 and x2, this function returns 1 if x1 equals to x2, and it returns 0 if the Hamming distance of x1 and x2 is exactly n over 2. The other output values are not defined. There is a SMP protocol with E bits of logarithmic communication complexity for the DJ function, but it does not satisfy the privacy condition. By applying a random affine transform to scramble the quantum messages, we can construct a corresponding PSM protocol that satisfies the privacy condition. The communication lower bound of omega n qubits can be derived by generalizing the argument of Diouf for partial functions. This is a summary of our results. We proved a communication lower bound of roughly 3n for two-party PSQM protocols with R bits for random functions. We showed a factor 2 gap of k-party PSQM protocols between R bits and E bits for the generalized equality function, which is a total function. We also showed an exponential gap of two-party PSQM protocols between R bits and E bits for the DJ function, which is a partial function. The next targets are as follows. In this work, we only discussed PSQM protocols with perfect correctness and perfect privacy. It would be interesting to show communication bounds in bounded error settings. Also, it is open how much lower bounds we can show if the parties share E bits. We showed a constant gap for the total function between R bits and E bits, and this is the same as the counterpart of the SMP model. Compared with the partial functions, this gap is much weak. So, it would be great if we could improve it even in the SMP model. This is the end of my talk. Thank you for watching.